All right, welcome back to GAME 2005 in the fall 2018 semester. That's at George Brown. We're game physics, and it's week 3, part 1 of our broadcast. This week we're talking about the chain rule, which is part of differentiation and integration, which is a new section altogether. So you're going to say, why did we not cover the chain rule last week when we were doing derivatives? It needs more time to discuss. It needs a little bit more effort when it comes to doing this stuff. You're going to see chain rule examples on your test. There's a 100% chance of that. All right. So there's, I'm not going to tell you that there's not going to be. There's 100% there's going to be chain rule stuff. So we need to talk about that a little bit. And then we're going to talk about integrals and what that whole thing is about. So there's one last rule we want to talk about, which is the chain rule. We know how to get the derivative of x to the 7, right? That is something like 7x to the 6, right? This is according to the power rule. This is kind of a review from what we've been doing the last little while. But how about something like the following? All right, so we have kind of an outer function, something to the 7, just like this, right? And then we have something on the inside, which is another formula. So it's like you have a formula on the inside, and then you have the formula on the outside. And if you think about what this is like for computer programming, it's almost like I'm passing in a whole function to another function, right? So I'm passing in a function. And it's kind of the same thing on the outset. So it's like I still do the power rule originally. So I take 7 and I pass it down in front, and then to the 6, 7 to the 6. And then what I want to do is take the derivative of the inside. So I take the derivative of the outside multiplied by the derivative of the inside. Okay, so that's kind of a different thing than you've seen before. And so it's a little tricky. It's a little tricky because you can have several layers of this. Okay, so think about this now. When it comes to the power rule, I could have a function that's inside of a function that's inside of a function that's inside of a function. And then how do you differentiate all that stuff, right? It's almost sometimes like what you have to do is, if you have a function within a function within a function, 3 layers deep, because you have this situation, the first time around, the first derivative is like this. Well, what this looks like is like you need to use some kind of other rule, right? The product rule, right? Where we have to take, f, the derivative of the first times the second times the derivative of second times the first, or whatever, that kind of thing. Well, that's what you'd have to do if you took another derivative of this one, right? Because basically you have a formula here, 10x, plus another one over here, and then plus you have this constant in front. So you'd have to use the constant rule. You'd have to, again, do the same thing with the chain rule, and then plus on top of that, you'd have the product rule. So it's a lot of rules altogether, and you have to try and figure out what to do first. The other thing that messed people up last week was the whole F and G thing. Right? Like, how do I assign F and how do I assign G? What do those things mean? People struggle with that. And think about F and G representing a whole formula. So F would be one formula, G would be another formula, another function, if you will. And then we're taking the derivative of the first function times the second, the whole second function plus the derivative of the second function times the whole first function, and so on. And for the product rule, and similarly for the quotient rule. So again, one of the things that people like to do is also use something called Leibniz notation, right? So I'm just going to go to the next level here. So here's the outer function, f, and then there's this inner function, g, right? And notice what you're getting is, so f at g at x, we can say, right? F at g at x, right? So it's almost like you have the inner function that's being passed into the outer function. And what that equals to is the derivative of f, right, at u. And where u is the derivative of the outer function. So the better way I like to look at it is this. This is Leibniz notation, but I like to look at it like this, where the first derivative of y, when you have some function u that's passed into f, right? U would be the other function, whatever that function is, right? And then you just want to take the derivative of that multiplied by the derivative of the outside. So the way I might remember it from a mnemonic perspective, and is one thing is, the derivative of the outside times the derivative of the inside. Okay, pretty simple, but it can get complex. All right, and it gets complex depending on the kind of examples we get. So here's some examples. So where y is equal to f of g at x, right? And we sometimes break it up like this, where we say u is g at x, and we can also say that y is f at u, right? So we take this whole u, sub it into, because g at x, if we say let u is equal to g at x, and then we can also say that then if u is g at x, we can sub in u there, just another variable to represent it. That's all it is. So what this does for us is it allows us to separate in our mind how to process one function over the other one, right? So example, we have y is equal to 1 over x plus 1. And you're like, okay, cool, right? And I have, I want to find that u is x plus 1, right, as an example. Then y, you can also write it as y is equal to 1 over u. And then you start taking the derivative of this function first, right? Similarly with y is equal to sine of 2x. Now this is without doing any kind of trigonometry identities. Okay, trig identities you can use to sine 2x is equal to something else. And we talked about this as well. But again, you could say that u is 2x. That's the inner function, right? And then you could just look at y is equal to sine of u. And if I was to take the derivative of y prime then would be cos of u times u prime. That would be your product, your chain rule. Okay? And it gives you some more examples here. So that way you could say, we'll cover this in lab a little bit more. But the idea is that you have an outer function and then you have an inner function, right? And different ways of representing that, right? So again, you have the inner function being 3x squared minus x plus 1, right? And then the outer function is some kind of square root, right? And then you're left with this kind of situation. And the reason why would they try and simplify it here on the right-hand side is so that students, when they're learning this stuff, can simplify it for themselves in their mind, because they can't differentiate the inner function and the outer function sometimes. They're like, which one's the inner one and which one's the outer one? I don't get it, right? But think about anything with brackets or any kind of outer function that applies some kind of mathematical operation to another function. That would be the outer function. For example, square root. If I square root of the inner function, square root is the outer function, right? And then the inner function itself, the inner side, is something that we have to do separately. Again, this is incrementally difficult when it comes to applying different rules at the same time. Yes.
I want to say different because in the first one you split out sine, but in the bottom one you just put out tan as opposed to tan squared.
Well, let's think about this for a second, right? So 2x, right? Remember, tan 2x is like saying, there's different ways of looking at this, right? Tan squared x is just a shortcut, right, for tan x to the 2, right? So that's what it's just a shorthand way of writing that, right? So it's really the same in some ways, but this is like you're taking the sine operation and applying it to an inner function, 2x. Imagine that inner function being something else, 2x plus 5, right? It might be easier to see that, right? And also the way this is written, because there's no brackets, right? So tan 2x looks like it's just one thing, but actually, if you think about writing this again, you write, or sine, and then parentheses, 2x. That's a different way of looking at it than sine 2x. Some people, they have trouble parsing it. Okay, so let's try this out. So what do we do here? So again, we'll just do this for the first time together, and then we'll go through it, right? So I'm taking it slow, guys and girls, because I don't want to lose you here. This is where a lot of students have trouble because of all the stuff that needs to be done. Okay, so again, if you think about what I need to do here, right? I'm really saying that y prime then, right, is equal to what? Some kind of square root operation, right? some kind of square root operation. So how can I write square root? Right? What's another way of writing square root? Something to the power of 1/2, right? It's another way of writing square root. So it's another way of looking at this, right? So square root, and if I was going to do cube root to the power of 1/3. And then, you know, there's different ways of doing stuff, right? So again, I could write this like this. So I can put brackets here, right? And then up here, I would make it so that it looks like this. So 1/2. 1/2. That is frustrating, but you know, we'll get over it. And so something to the power of 1/2. So I could rewrite this as 4, and then again, bear with me because I want to make this clear as I can, right? Plus 3x minus 1. Okay, so that's where it starts off. So let's not write this as y prime. Let's just write this as y for now. Okay, so y then would be equal to this, right? You could just rewrite this thing. So now you have clearly an outer equation, right? An outer formula, something to the 1/2, right? And so you could see this inner part here as u, right? So forget this little mark here for a second. This is where I would do the next piece, okay? So really what I could do is I could rewrite this whole thing as, if I say let u then equal to this part. Oh, it's not going to let me. Let's just see if I can do that one. Cut that out and then just kill this part here. Yeah, so we can say, if you can imagine that, if you say let u is equal to this, right? When it comes to, I can rewrite this, let u is equal to that, and then I can rewrite y, right, altogether, right? I can rewrite y. Let's see if I can do this. And again, don't worry about the little box right now. As u, right, to the 1/2, right? U to the 1/2, where u is equal to 4x squared plus 3x minus 1, right? That's what they're saying with that notation. And it's the reason why we do this is not because you can't figure it out on your own really quickly without doing u, but when it becomes more challenging, right, you have a method, a way of isolating both equations, and from an understanding perspective, you know, how to put things together. So let's put these three things then on the side, right? Here's the stuff on the side. And what would I do now? Here, I'll take this part. So I'm going to go down from here. Let's do one more step here. What I do here, if I wanted to find out how do I get y prime then of u to the 1/2? What do I do? What rule do I use? This should be reviewed from last week, guys. Product rule. Or, sorry, power rule. Power rule. That'll be all right. Power rule. Yeah. So what you do is, again, you take 1/2 and you subtract 1 from it. So it's still like normal. So up here in 1/2, you subtract. See if I can do this properly. Subtract 1. So that will be the first thing you do. And then I take 1/2, this 1/2, and multiply it by whatever's in the front. So let's see if I can pull that off. So 1/2. I'm just rewriting it so you can see this. So this is the answer, right? 1/2 u times 1/2 minus 1. So that's 0.5 minus 1, which would be negative 0.5. So it'll be negative 1/2, right? So negative 1/2 is the answer. I'm just going to get this out of here. Again, I'm just taking it really slow for people to understand what I did, right? Because you have 1/2 and you always subtract 1 when you do the the power rule, right? From the top right corner. So if you had a negative, it'd be more negative. If you have half, it'd go to negative 1/2, right? And I pass 1/2 over here. So this is the answer from the outer perspective. Now I got to find the, I got to do the next part, which is multiplied by u prime. So again, I would multiply by, if I can do this, u prime. U prime. U prime doesn't like me. So let's just try this again. U prime. Sure. We'll use the really weird notation u prime, which is, I don't understand why it's doing the same thing. U prime, there we go. So that's what the answer is. Now, please don't think that u prime is multiplied by 1/2. It's like literally these are two different portions. So I'm going to see if I can separate them for you. So just for clarity, not for any other reason. I don't know if I can do this properly with this situation. That's too much up there. Right? That would be something that would be closer to where we are. So u prime. So we got part of it. Now we gotta sub in what u prime is. And sometimes what we do is when we do this part here, we actually calculate u prime first. So we kind of do our pre-work before we get up to that point. So again, again, guys, please forgive me. I'm trying to go really slow here, believe it or not, so that you guys can get it. And most of you probably already get it, but you know, it's just I want to make sure that we're all good, because this is where I have a lot of questions with regards to chain rule, and I have a lot of concerns on the tests when it comes to chain rule as well. Like they're like, I didn't quite get the chain rule part. I totally forgot how to do it, and it doesn't matter how often I go through this. It's like the most difficult piece to remember. So, okay, so if u was 4x squared plus 3x minus 1, then u prime is?
8x plus 3.
8x plus 3, because you take the 2, subtract 1 from it. So it would be x to the 1, which is just x, right? And then take the 2 multiplied by the 4, which would be 8. So you have 8x, right? And then 3x is actually, you can picture it as 3x to the 1. 1 minus 1 is 0. X to the 0 is 1. Anything to the 0 is 1. And so you are left with just 3. So that is that part. And then, of course, this is a constant. Constant is eliminated because any derivative of a constant is 0. So this part is like this. So that would be u prime. Okay? So I did it over here. So now you know what to do over here, right? You just like sub in u prime over here. So again, I'll go here, copy and paste, put it down here, and then sub in u prime. And I'm going to get a question like this, but I'm going to answer it ahead of time. Do I have to do u's? Do I have to show u's and this kind of stuff? Do I have to do this method? Or can I just figure it out? On a test, do what you want, right? I mean, you're going to have A, B, C, D, E. But it's nice to show your work. So that's the answer, by the way. Y prime is equal to 1/2. Oh, wait, we have to actually sub in u. So we don't eliminate u, right? U is still around. We still need this part, right? So we still have the original 1, right? It's just that we multiply it by the outer, right? So that's what it would look like. It looks complex. It looks complex, but actually it's not, right? You take the derivative of the outer, keeping the inner formula the same. You haven't touched it. Multiply by the derivative of the inner. Yeah, that's how it is, which is what we just did. Okay, so that's kind of the way to do it. I would try and write out your solution for a test if you to get part marks sometimes. Here's one that I left from last time, and it's actually up on your on the PowerPoint up online as well. I think maybe not, but basically. Here's a quick way of doing it. So let u is equal to sine x minus 5x to the 3rd, right? That's the inner. Y then would be u to the 6th, right? Plus cos x, that's the y. Y prime then is 6 u to the 5 times u prime minus sine x. Why minus sine x? Because this one, cos x, becomes negative sine x, which is up here. And then you sub in what you know. You sub in u and u prime, right? Now I didn't make a u prime, but if I was going to make a u prime, it would be just cos x minus 15x squared, right? That's what u prime is down here, okay? So you sub in there, and then that's your answer. Another reminder for your test, please do not simplify, right? So I don't want you to go further than this step. Could you go further than this? Absolutely. And maybe in a full math class, if this was a math class, not a physics class, and not a physics for game class, maybe your professor will get you to, to do all the algebra involved and figure this out. And so the test will be different. But this isn't a math class. This is, game physics. And we're learning a little bit of calculus just so that it helps you to understand, the relationships that we're going to learn in physics. Okay, that's what it does. So questions around this, the chain rule. All right, We're going to get some more difficulties happening. Okay, so I'm going to handle these a little bit in lab, but think about this one. So y is equal to sine of 2x. Well, then u is 2x, right? And if y is equal to cos of x minus 1, then u, the inner function, would be x minus 1. And then y is equal to tan 3x, then u is equal to 3x, where u is another function, the inner function. Okay? So pretty straightforward stuff. All right, how about this one? What do I got going on there?
So u is x to the 5.
Okay, let's write this out. I want to experiment with this. Again, remember I told you, it's just going to get messed up from here, right? Well, let's. I want you to think about this really carefully, right? Because, you know, I'm going to try and pull this off with you guys a little bit at a time. So there's some issues here, right? So let's figure this out. So we can say that u is equal to what then? Could I say x to the 5? Is that possible? Let's assume you're right. Let's assume it's x to the 5 and put that in there. So here's x to the 5. All right, so let's say u is equal to x to the 5. Okay. And we can also write then, what would be u prime then? If u is equal to x to the 5, then u prime, common notation. I wish there was a quicker way of doing this, but unfortunately there isn't a great way of showing this without me actually physically drawing on a tablet or something, which I could do, but so this is like 5x to the 4, right? I'm already doing it backwards. Yeah, so 5x to the 4, right? Wouldn't that be correct? So u prime would be 5x to the 4. Okay. So could we say that then, which I get another one, could I say that y prime then, y prime is equal to, okay, so how do you do this now? Like what the heck? Which is the outer function? What's the inner function, right? Are you right?
The outer function out of 5.
So think about this. What's the way of doing this thing, right? You know, so like I tried to go with what you said, right? What you saw x to the 5 as the outer function.
It is 2 to u, so that you have to take the derivative of 2 to the u.
So what you're doing is actually,
And then
if you say
by u derivative.
let's do it. So 2, you can do this, right? So again, it's just a matter of how you perceive this thing. There's many ways to write this equation, by the way. So if I go 2 to the u, right? 2 to the u, and then times u prime, right? Because that's what I want. I want the derivative of 2 to the u, right? And then whatever that is. But is it 2 to the u? Don't you take u and then minus 1 from it? Because that's the product rule, right? So, or power rule. U minus 1 and then take u in the front and then,
No, it's not that.
I don't understand. Like, that isn't that what we do? That's the pattern, right? Think about this clearly.
No, that's not it.
Because if I was to multiply,
those formulas that was perhaps in the second.
yeah, hold on a second. Let's go over here and write this down out so people aren't confused. And then times u to the u prime, right? So again, what you're saying is it should look like this: u prime, right? 2u times u prime. Okay, but this 2 to the u, right, as an example, you take the derivative of the outer, right?
Actually, it should be 2 to the u prime multiplied by u prime. That's the original.
Should it?
I mean, I'm just saying for this sake.
Well, think about this. You guys got
It's the derivative of 2 to u in function of u.
let's go put this back. So let's like not have this for a second. If I was just going to rewrite the equation that I want to derive from, is it this equation, 2 to the u?
You know that if we were talking in Portuguese, it would be easier for me to explain that to you.
I'm sorry. I'm not Portuguese. I wish I knew how to speak the language. I love languages, but I can't. Especially computer languages. Well, okay, so if this was something to the u, and where u is a value, like 3, right? Then we would carry down the 3, and then it would be u to the minus 1, would it not? Think about it, right? This is, you can't do what you're saying, like, 100%, right? If I was going to do this, so ignoring what u actually is for a second, if I said y prime then, right, is equal to what? It would be u, right, in front, because you would take u, and then u to the minus 1. Would not that be the case?
This is the derivative of that?
Of course, right? It's following the pattern, right? I'm not talking what u is yet. I don't know what u is. I'm just saying, look at the original power rule. The original power rule is exactly this, right? Something to the end.
Power rule takes x as the base,
Ah.
or u as the base.
But 2 is not
this
an x.
formula, u is the exponent, so you can't use the same rule.
You're right.
You're crazy.
I'm not crazy. And you're right, 100%. But people will do this, right? They'll go, wait a minute.
They're crazy.
No, because they're not seeing it. They're looking at this as 2 as x, and 2 is not x. You can't look at it like that, right? So because if you go back to the previous formula, it's not 2 to the x, it's x to the 2, right? So if this was written differently, if this was y is equal to x, to 2 to the 5 or something like that, that would be totally different. It would be like the outer and then the inner, right? But this is not the case. This is 2 to the x to the 5, right? So how do I rewrite this one? This is a different thing. What's the case that I'm looking for? So let's erase this stuff. So going back to this x to the 5, that's definitely an inner equation, right? But it's 2 to something, 2 to the something, right? And whenever you have a constant, right? If I said 2 to the 1 or 2 to the 5, and I tried to take the derivative of 2 to the 5, what would be the answer? 0, right? Because 2 to the 5 is a constant, right? And any derivative of a constant is 0, right? But you have a derivative on the inside. And if you take the derivative of the inside, whatever that is, multiplied by 0, you get 0, right? So that also presents an issue. So how do you do this one? Anyone have a thought around this thing? 2 to the x to the 5?
So there is this derivative table here, and it says that a to the x equals to a to the x log.
Yes, it's a logarithm. It's a logarithm. Yeah. And if you actually look at the previous PowerPoint presentation, it showed you that. So if I go to, again, I'm pointing this out because it can be deceptive, and you might be fooled into thinking that it's one thing when it's something else. Now, curious, do you think that I might give you a question like this? I think there might be one that's on there like that. But we're talking about it. We're discussing it. So it's not like you're, I'm trying to fool you or anything like that. It's just, here it is. Here's this what we're talking about, right? So the case is not what we thought it was. We forgot, right, what the thing is. It's this, right? When you have a case where the value of 2 to the x, right, and if I want to find the derivative of 2 to the x is the logarithm, right, of 2 multiplied by 2 to the x. So you keep that, right? So that's the outer derivative, right? That's the outer function, right? And that's what we need to do, log of 2 times 2 to the x, right? And then once we have this pattern, we can apply the inner derivative. Okay, that's the answer. Okay, does everyone see that? So the reason why I brought it up is because deceptively it looks like it's x to something, and people get confused about that, but actually it's not. It's this, right? We haven't covered this in lab last week. I didn't go through log functions, so I'm pointing it out because it's an anomaly. Yeah, we see this sometimes, but if you ever see something like a value to the x, and I ask you to take the derivative, it's going to be a logarithm. Okay. So that's from last week's PowerPoint on page 19 for those people who want to reference that.
But does that really solve our problem if you get the same, item that we don't know what to do with?
No.
We still have the a to the x in here. So
No, but that stays.
Okay, so that's.
So a to the x doesn't go away. That's just like the e to the x. See, e to the x is equal to e to the x. It's just an identity, right? So whenever I take the derivative of e to the x, right, Euler's constant, right, to the x, it stays. It doesn't go away. I don't eliminate it or derive it in any more ways in this, right? So going back to this, then we know that it's going to be log 2, right? And 2 to the x to the 5. That's what will be the answer. That's the first part. So again, if let u is equal to x to the 5, then we can rewrite this equation, right? And I know, guys, it's I'm sorry about this. I'm going about it in a very long way, but it's not because of I want to bother you in any way. It's because I want you to see the problem potentially and try and deal with it. So it's, again, I'm just going to insert log, and can I? Radical, what was that?
Third from the right, limit and log.
Limit and log, third from the right. Thank you. Yeah, so this is the one I want to use. So log 2, right? Because that's what the 2 is. So 2 goes to log 2, and then x to the 5, because that's not going to change, right? That is the first derivative, x to the 5, right? So x to the 5, that's the first derivative of the outer, and then multiply by the derivative of the inner, right? So again, I'm just going to put brackets around all this so you can see the solution.
Are you sure?
Absolutely. Right, times,
Oh, I thought it was going to be log 2 of 2x, 2 to the power of x to the power of 5.
no, x to the 5 is the number, right? Right, so actually, yes, you're right. It should be this whole thing again. Yeah, because yeah, no. You're right.
I know this can be deceptive.
No. You're absolutely right. Look. I'm telling you. I'm sorry. You know, when it's something. You know, there's two things. When you're coding live. So if I'm doing computer code live and I'm doing this live, you know, you got to think on your feet, which is always difficult. So I do apologize. Right. So yeah. So it's actually looking like this more like 2, and again, we'll just do this again. X to the 5. Right, and then multiplied by the derivative, which is 5x to the 4. Right, that's what I was going to do. So that's the answer. And you might look at it and go, I have no idea what this means, right? But what I want you to go, where I want you to go with this is think about patterning, right? And once you see the pattern, then it should make it easier for you, right? And as you saw, even for me, it's not like you can't make an error. A mistake in thinking, but the great thing is that we've talked about it now and it's recorded, and it can maybe help you with your test, which is what I'm hoping. All right, oops. Here's the last one. Find the derivative of y, where y is equal to 5x minus 2 over sine squared x plus 10x. What do you do here? Yeah. Sorry.
The formal one.
Oh.
And third question, let you is it 2 to the x.
Okay, and then to the 5. Okay, that's another way of doing it. Yeah, you could do it that way. So if you said you want to say u is 2 to the x, right, and then everything to the 5, but would that be correct? All right. Is it commutative? Is the question, right? Can you do 2 to the x to the 5? What if I do, let's sub x with some other number. Let's make it 2 to the 5, right? 2 to the 5 is what? What's the answer? 2 times 2 times 2 times 2 times 2, right? So 2 times 2 is 4 times 2 is 8 times 2 is 16 times 2 is 32, right? Is that right? 32. So 2 to the 32, what's that? I don't know.
2 to the 32 is about 4 billion.
Can someone give me the number? Right? Actually, I can probably figure that out too. Right, so if I want to find 2 to the 32, I do this again on this bloody calculator. It's like x to the y. Here it is. So, what was that?
It's approximately 4.3 billion.
Okay, great. So you figured it out. So now let's do the other way around. So let's do, you know, 2. So we said that, you know, 2 to the 5 is 32, right? So let's do the other way around. So how do I figure out the other way around so that I know that it's right? So what's 2 to the 5 on the outside? 32, right? And then what the heck do I do on the inside? Like, how do you do that, right? how do I make it commutative this way, right? So 2 to the 5 we know is 32, but how the heck do I do 2 to the, to something else? 2 to the x to the 5. I don't know how to figure that out, right? So my view is that you could do it the other way. I recommend you do it my way, the way I showed you, because it'll prevent confusion, right? All right, let's go on to the next one, okay? So if you go to 5x minus 2 over sine squared x plus 10x, what do we do here? How do I figure this one out? When you look at this, if I didn't know anything about the chain rule, what would I try and do? And I'm gonna leave this for a lab. I'm not gonna figure this out right now, okay? Because we have to move on.
But that only can definitely use the division
Quotient rule. Yeah, so use the quotient rule here because I have the top over the bottom, right? However, we also have right here an area where we have to use the chain rule, right? Or you could use a trig identity, right? So to get rid of that, so you don't have the chain rule anymore, right? If you can. However, it's sine squared x. You might find that it's not so easy to get rid of. So again, this would be like sine x squared, where something is x to the 2. That's what it is. And the outer is x squared. The inner is sine x, right? Or, that's what you want to try and do. So it would be the bottom part. So it would be the derivative of the top, which is 5x, minus the whole bottom, sine squared x plus 10x, times the whole bottom, minus the derivative of the bottom, and this is where we get into it, right? Derivative of the bottom would be, I have the chain rule plus 10x. So the chain rule plus 10, because 10x goes 10, because 10x becomes 10. The chain rule is something to the 2, so it'd be 2 times sine squared x multiplied by cos x, right? That would be the outer, and multiplied by the inner. And then all over sine squared x plus 10x all squared. Okay, that would be the answer. We're going to go over again in lab, but again, sometimes what you have to do is multiple operations where you have, a function within a function within a function, or 2 rules that apply, and you have to know when to apply things in order. So that's chain rule. And that's why I left it out until this week, because it requires a little bit of attention on its own, right? And then last week I had to give you some examples of how to use regular derivatives. By the way, in high school calculus, last week's lesson probably took like 2 months, right? We did last week 1 week. And this week's lesson probably take, another few weeks, right? Because we did many more examples. So, that's why, the course is kind of split up this way. Okay, so integrals. So we talked about derivatives last week, and that is taking a formula and then taking the instantaneous velocity or instantaneous acceleration or instantaneous value at some point in time. Okay, that's what really what it's about, right? And we talked about derivatives. The real reason why we want to use derivatives is to help us when it comes to physics, especially for position, velocity, and acceleration relationships. Okay, that's what they're for, right? More than anything. There's other motion that we also want to capture with derivatives. But here we have something of an opposite relationship. So I have this question: how do we find area under the curve, right? So I have a curve as an example. I want to find the total area under the curve, right? And a good question of this is if a car travels 60 kilometers an hour for 1 hour, how far does it go, right? 60 kilometers an hour for 1 hour is a constant rate of speed, right? You hear what I said? Constant rate of speed, right? So that means that it's traveling at the same rate. When I talk rates, it's, kilometers per hour, right? Or miles per hour, or meters per second, rates, a rate of change, right? And because it's a constant rate of change, that means it's not fluctuating. So the velocity would be constant here, a constant velocity, right? And it says, how far does it go? Far is a position function. So I have velocity, 60 kilometers per hour, and I want to derive position from velocity, right? Actually, not derive. I want to integrate I want to go back up the chain and find out what the position function is. But there's a problem with this approach, which we're going to talk about in a second. So how do I do this? Well, here's 60 kilometers an hour, right, as an example, and see the area under the curve is nice and rectangular. Yay, right? 60 kilometers an hour multiplied by, 1 hour, 60 minutes, and then you have the area under the curve. Nice. But, what happens when you have this situation? 60 kilometers an hour for the first 30 minutes, and then 70 kilometers an hour for another 30 minutes. How far does the car travel then, right? So now I have two equations, right? I have an equation for the first part of the trip and the equation for the second part of the trip. And then the total area under the curve, if you were to see this, is like literally drawing two rectangles. So I have one rectangle here, right? Roughly, please forgive me for my drawing skills. And another one over here, right? Which is what we would add up together to get the total area under the curve, right? And the curve is not really a curve, it's just two lines, right? A speed and then another speed. We all see this. So this is easy stuff. We can figure this out without integration. We can just add things up, right? It's, length times width equivalent, right? It's speed times time, right? And that's what velocity is, distance over time, right? And that's how you find the total distance, or kilometers per hour or whatever, right? And that's how you find the distance. But what about this, right? What do you do here? And this is where we find that we can try and use some rectangles. So maybe I can use a rectangle that is roughly like this. And I'm just trying to roughly draw this stuff, guys. And you can see that I can try. This is what they used to do. They kind of made an estimate of the area under the curve. And, as an example, I'm using pretty big rectangles here. And maybe if you really want to, you could use smaller rectangles. So if I zoom right in, maybe if you get the resolution a lot higher, you can use a much thinner rectangle like this, and then maybe much more of them. And then what you do is you take all these rectangles under the curve and add them all up together, and you get a rough estimate. You're still going to have this little notch right at the top because the rectangle looks like this. It's not like a curve. But if you get fine enough resolution, right, it'll be very close to what you're going to get, right? So I get lots of rectangles under the curve. You add them all up together, and you get the total area. Yeah, that was the old way we did it, especially back thousands of years ago. Right? To kind of find the rough area. And it would be pretty close. Especially when it comes to carpentry, it would probably be close enough. Okay, that's the answer. So this is one way of doing it, but really not a great way. It's not very accurate. So we need to develop some kind of method to find the area under the curve. And we can start with working with this idea of x squared, like this. This is x squared. And try and find some method that we can work backwards for all functions. And that's what when we start deriving, area of the curve, they tried stuff, and I just did it. You can try 2 rectangles or 5 rectangles or 100 rectangles. We can make as many endpoints as we like. And at the end of the day, we're going to get closer and closer to the area. Here's an example of what I was trying to do, right? And you can see that the resolution here is not that great, all right? It's like big rectangles, and there's areas like up here, which is overestimated, right? And there's areas over here which are underestimated, right? Overestimated goes outside the curve, underestimated goes below the curve. You're going to get areas like that, and you're going to get some error, right? Whatever that error is, okay? So again, better area you're going to get with more rectangles. So when they started doing this, these infinite sums of rectangles. And by the way, we're not going to, Riemann sums is what they're called, right? And if you were to do high school calculus, you might do Riemann sums. I'm not sure if you guys remember that or not. Maybe you don't. Maybe you never did it. That's fine. But basically what you do is you try and do a lot of the integration stuff as a pre-step to understanding integrals. You do a bunch of these draw actual rectangles and try and fill in the areas and try and literally work out what it's like to do that. Of course, we don't have any time. We have like a week to do all this stuff. So I want you to take my word for it that basically an infinite number of rectangles, small enough, could be very close to finding the area under the curve. Okay, and you actually would add them all up to do that. So the sum, again, where n approaches infinity of all the rectangles, right, that you need, is where you're going to get kind of the total area under the curve. And the idea is that what we want to do is take the antiderivative. So we've taken the derivative going down one way from position to velocity. And now we have position, and we want to kind of figure out, well, what was the velocity to get us to this, what was the position to get us to this velocity if I was going to take the derivative? All right. Now there's a wrinkle here in that sometimes the position function, actually quite often, has a constant, right? Think about the constant. So if I said the position function was x squared plus 3, what would happen to the 3? Gone, right? How do we get 3 back? You know, how do you figure that it's 3? It could be 3, 5, 10, infinity. You don't even know what that number was that you added together. You can certainly go back the other way. If you have something like, you know, 2x as the derivative, and you want to take the antiderivative, you know that you're going to go back up to x squared, right? Because x squared, take the derivative of x squared, you're going to get to 2x. So if I have 2x as the velocity function, and I want to get back to position, I know that part of the position function then, it must be x squared plus some constant c. Some constant c. And we don't know what that constant c could be. It could be any number, right? It could be any number. Do you see that? Right? Because we've come down from an equation that has some kind of constant that could have been eliminated through a derivative, even if there wasn't a constant, even if the constant was 0. So I could have had an equation like 2x squared, or sorry, let's go with x squared. X squared plus 0. 0 would be the constant that would have been eliminated. So we don't know. It could have been 0. It could have been infinity. We don't know what it was, right? Chances are it wasn't infinity, though. If it was infinity, then we wouldn't have the derivative that we do. Yes.
That was just going to be my question of curiosity. Can you actually divide
Infinity.
Yeah.
Derivative of infinity is infinity, I think, right? Or infinitely 0. How about that? Okay, yeah.
About that definition, is n the number of rectangles?
Yeah. So basically, again, the area A of the region S that lives under the graph of the continuous function. Remember, continuous function, so not broken up function, where you have 3 different kinds of formula, right? Is the limit of the sum of the areas of the approximate rectangles. So A is the area under the curve, right? Where limit as n approaches infinity, infinite number of rectangles, right? Of the area, each of the rectangles. There's one rectangle plus another rectangle plus another rectangle, and then you can sum it up as each of these f to the x I, right, or to x to the star, whatever it is the derivative of this, right?
So what defines the width of each rectangle?
It's usually the x value, whatever the x value is, right? So the width would be, for example, if you were going to take velocity over time, time would be the width, right? So velocity times time, you're going to get distance, right? Okay.
It would be delta x in that case, wouldn't it? Changing.
But let's keep going, because otherwise we're gonna miss our window for explanation, right? So if you think about this, then if s at t is the position function, and we know that v at t is actually s prime at t. So s of prime at t would be the position function, the derivative of the position function, right? So we know that velocity is the derivative of the position function. That's what this is. That's what this relationship is sharing with us, right? So we can say then that when we take the antiderivative of f on an interval I, interval meaning the interval, and when we're talking about intervals, we're talking about time usually, or distance, or something like that. All right, or sometimes it's acceleration in time, right? Is this where we take the function at x, f at x plus c, where we don't know what c is. All right? So the original f at x, whatever that function was, where c is any constant. And where it says, and I know this is kind of funky to look at, right? When you look at any constant, so going back to what Uval says, right, could it be infinity? Yes. Chances are not, because if it was, then it would mess up our original derivative in the first place. Would I give you an infinity as something to figure out? Hell no. It's not going to be on your test. It's out of scope for this thing. But it could be using this function because it says any constant, right? But is infinity a constant is what you're should be asking me, right? Is infinity a constant? Anyway, we'll talk about those esoteric things in lab. It's almost like I would say bordering on the on philosophy. All right, so if you look at this one, so here's a couple of things that I wrote down. Again, I kept this from last time, right? Is So if I have if f prime at x is equal to 16x7, 16x to the 7 plus 4x, then what is f of x? The antiderivative. So I've got the prime, and I want to work backwards. That's what integrals is all about, right? I know then that I would do the opposite of the power rule, right? So it's something that multiplies to get 16, and when I subtract 1 from it, I get a 7. So if I subtract 1, what I want to do is add 1. So 7 plus 1 is 8, right? And if I take 8, whatever the number is, and divide it by the original number in front, right? Then you're going to get 2. So that's my method. My method is add 1 to the exponent in the integral form, right? So 7 plus 1 would be 8. Take that number, whatever it is, and divide it by the number that's in front. Okay? And then you're going to get 2x to the 8. So that's the first part of getting this part. Okay, 4x, again, same thing. So I have x to the 0 here, or x to the 1 here, and I want to add 1 to it because we subtract 1 going from the derivative. So x would be x to the 2, and I take 2, and I take 4 divided by 2, and I get 2. Right? So now I have 2x squared. And then I add c to it, always, in this form. Okay? Why? Because it's some number c that I've erased because of the derivative. I don't know what that c is. It could be anything. Okay? Are you with me? Because if we don't, from here, this is where derivatives, this section here, this week is the hardest part of calculus. Always integrals screw people up because it's going backwards, right? And going backwards, you know, it seems to be a lot harder for some people to understand. Here's another example, all right? Another example. I got x to the 3, right? That's the derivative. I want to find the antiderivative, the original equation, f of x, right, as an example. So I know that I'm going to add 1 to the exponent going back up, so it's going to be 4. And I have 1, an imaginary 1, in front of x, so I divide it by 4. So 1 over 4 times x to the 4, plus some number c, some constant c. And that would be the antiderivative. Do we see that? Okay. Let's try a couple more for us. Okay, what do you do here? I'm going to start asking you guys because let's follow my method here. So I have x to the negative 2. What's the first thing that I should do to try and get the antiderivative? Add 1 to the exponent. So what is that? -1. X to the negative 1. Okay, fine. Now I take that negative 1 and I pass it down in front of the imaginary 1. Right? So negative 1 over negative 1 is negative 1 times x to the negative 1. That would be the answer. That would be plus c. Can't forget that part, right? It's plus c because it's some constant, right? Let's try this one. So I've got x to the 1/2. What do? Add 1 to it, right? So now I have 1 and 1/2. Okay. You could also rewrite that as 3 over 2, right? 3 over 2. So I take that 3 over 2, and then I divide it by 1. 1 divided by 3 over 2. So it's actually 1 divided by 3 divided by 2 over 1, which invert, when you invert to multiply, which is 2 over 3. So 2/3 times x to the 3 over 2, or 1 and 1/2, right? Plus c. Thank you, right? So those. I want to go over those again in lab today, right? So I'll actually physically write them out for you guys, right? We'll do it in class. Okay, are we clear with this stuff? This is the first antiderivative. What happens, though, if I want to take the second antiderivative? And I'm not going to get there yet, but think about this now. Instead of having velocity, I have acceleration, right? And I want to go all the way back up to position. How do I do that, right? Well, chances are acceleration is either going to be some value, 5, as an example, right? I have a number 5. If my acceleration is 5, what would be my original function, my position function? Think about this. Let's work it out in your head. So if it's 5, if I go one step back up, right, then it would be probably 5x, right? 5x plus c would be my first antiderivative, 5x plus c. Because when you go back to velocity, you might have a constant component as well in velocity. Okay, so 5x plus c is now your first antiderivative. I want to go to the second antiderivative, which is into position. But I have this plus c. What the heck do I do with that? Well, you add d to it. That's what you do, right? So 5x plus c then would be, if it's 5, x to the 1, right? I'm just doing this all in your head, right? So I add 2 to it, add 1 to it, so x to the 2, and I take 5 over 2. So 5 over 2, x to the 2 would be that part. Plus I have c. C is like, I have to multiply it by x. Cx plus d. And that is your second antiderivative, right? Because you don't know what c is and you don't know what d is, because you could have had two constants that you have eliminated through the constant rule, right? Just saying. You're going to get there, c and d. And you're like, c's and d's, I don't know what this means, you know, kind of thing. And they're just two constants that we don't know what they are. All right. So here's another example. I've got, find the antiderivatives. You might see this in your test, right? And it says more complicated functions use the following properties, where it says k times f is an antiderivative of kf, right? And f plus g is an antiderivative of f plus g. So basically what you're doing is you're taking two separate antiderivatives and trying to figure it out on their own, right? So what this means is if I have more than one term, I could take the antiderivatives of each term separately and add them all together, just like we did with derivatives, right? So here we have 2x to the 8. Again, we'd add 1 to it, which is 9. And then you get 2 over 9 times x to the 9. That's the first term, right? Okay. Plus 3x to the 1. x1 plus 1 is 2. 3x to the 2 over 2, right, would be the second term. Okay, 1. In order for me to have a 1 here, there should have been an x in front of it. That's this, because 1x is equal to 1 when you do take the derivative. So that's that one. Plus c, some constant value. All right? Sorry? Why? Because it's a constant. And you don't know if there was any or not. And so we assume that there is. Right? We must assume that there was some constant value. Otherwise, we can have a huge error in our graph, right? If we actually graphed it out and we forgot the plus c, that means it would shift one way or the other, right? Depending on the type of graph we had. So we must have this plus c in there. All right, one more here. So let's just talk about this again. How do I find the antiderivative? So I want to find f of x. If I have f prime at x, I want to find f of x, the antiderivative, the position function. If this was the velocity function somehow, what would be the position function? All right, so 5 sine x. So that means that 5 was in the front somehow, and then I have sine x. Now this is kind of funky, right? What would be the the antiderivative of 5 sine x? That's the first part. Let's look at that one. Well, the derivative of sine x is cos x, and the derivative of cos x is negative sine x. So there must have been a negative sign here in the first place. So something like negative cos x must be in this term, right? Times 5. So negative 5 cos x would be 5 sine x. Remember, 5 is the constant that would be taken out, right? So we wouldn't multiply that. So that would be the first part. How about this one? So this is easier. So negative 1/2. You add 1 to it. So that's positive 1/2, right? So, and then you divide 2 by 1/2, which is actually multiplying it by 2. 2 over 1 over 2, which is like 2 over 1 over 2 over 1. Multiply, you inverse and multiply, and you get 4x to the 1/2, which is like saying 4 times the square root of x, right? And that's your antiderivative, plus c, if you don't remember that one, right? Guys, we'll go over it in lab. Okay, I'm going to show you the examples step by step and how to do all that stuff in lab. All right, let's go forward. So we have cases where some useful anti-differentiation formulas that are here that are going to help you. Okay. So again, what we have is this idea of when it says lowercase f, this funky f, at x means almost like f prime at x. Okay, so there's different ways of writing this. And if f prime at x, where x is to the n, where n cannot be -1, we have to put that in there because if you have a negative in the n, that would be something that's undefined. We cannot do a negative exponent, right? Some negative value for n. Okay, so x to the n then would be, like it says here, I would add 1 to the n and then divide by n to the n plus 1, which is exactly what we've been doing. So this is the first thing we've been talking about, this thing here, okay? If the derivative is 1 over x, then we know that you're going to get something like the natural log, or ln is what you say, ln of x is the answer, all right? So these are kind of identities, if you will, to help you with some of those antiderivatives, right? The antiderivative of e to the x is e to the x, because you would have got e to the x in the first place, right? That never changes. So that's cool. The antiderivative of sine x is negative cos x, and cos x is sine x, and sec squared x is tan x, and so on, all right? But remember, this is just for each term. You still must add plus c on the end of everything. So if I find the antiderivative of f prime at x, where f prime at x is equal to 7 sec x tan x plus 1/4 x to the negative 6, how would I approach this problem? This is a different thing altogether, right? So you look over here, sec x tan x, right? This is equal to sec x, secant x, right? The 7 stays where it is. So 7 sec x, right, is this part. Okay, plus, again, 1/4 x to the negative 6. Negative 6 would become a negative 5, right? Negative 5, because you add 1 to it. And then you take 1 over 4 over negative 5, right? Which is negative 5 over 1, which you invert multiply, which would be negative 5 over 4, right? Plus c. Thank you for that, right? And this one here, again, we're just talking about it, but I want you to visualize it in your head what to do. I have something over x. It looks like this, right? It's like 8 times 1 over x, right, which is equal to 8 times ln x. That would be the first part. Minus, and I've got this situation, right? I got this situation. Whoa. Okay, what the heck do you do here? Well, look it over here. You have this, situation right here, right, where I have 1 over x squared, right? 1 over x squared, but you have this square root sign. Can we do something about that?
Middle one there.
Right? And here's the one over here, right? We have this one and we have this case. So this case is like saying it's 3, the constant, times 1 over root of 1 minus x squared, right? Which is this. And that is equal to 3, because you take the constant out, times sine to the negative 1x, right? So 3 times sine to the negative 1x, and that's how you'd form this one, plus c. All right, so I'm giving you these quick hits identities. However, you can add more when you make your own cheat sheet. Next week, I'll be releasing a cheat sheet that I have for you. You'll take it home, just as a reminder. You'll make it your own. You'll add your own formula to it. You can add problem examples on the front if you want, but it's only one side. You can only have a one-sided cheat sheet that you must handwrite with your name and student ID on it. Okay, so don't pass this to anybody else. It's your cheat sheet. On the test, week 5, which is 2 short weeks from now, you're going to give me that cheat sheet with your scrap work, with your work that you do on the test. I'm going to collect those 2 things from you on the test day, okay? Okay, one more thing is, if I give you a cheat sheet, some may choose to bring in their own completely. So you may ignore my cheat sheet if you want, okay? So I'm going to give it to you, say, hey, I recommend these things on there. But some people said, well, what if I just want to write my own? You can do that. I'm fine with it. So if I give you mine and you take mine, transcribe it really, really small, and make your own and bring it in handwritten, I'm good. Okay? So that's 2 options. Some other people have micronized mine. They've taken mine, really made it small by photocopying it, making another sheet, and then it's mine, really, officially, and then writing on top of that, that's fine too, right? But your part, your own part, that doesn't include my stuff, must be handwritten, okay? So if you're going to redo your own cheat sheet, I don't want an Illustrator-based cheat sheet or Photoshopped cheat sheet or some kind of photocopied multiple times and micronized cheat sheet or blue and red and some other color where you can wear different glasses cheat sheet, right, to detect it. That would be interesting and innovative, but please don't do that. That would be 0. I know, it will be exactly some weird, black hole cheat sheet. All right, so here's something, integral rules. So we talked about so far some kind of, identities, and these are other ones. You can also use these. This might be something you might see on your cheat sheet. Notice that there's this little funny looking L or F, an F and an L, or an F with without the cross there, and this little thing. It almost looks like a weird L, right? Or an I. I don't know. People look at it different ways. This is the integral sign. And when you see this, the integral of x to the n, right? Think about, you can also, in your mind, think of this as the antiderivative, right? The antiderivative, because this would be the derivative. So if the derivative of x to the n is nx n minus 1, the antiderivative, or the integral of x to the n then would be x times n plus 1 over n plus 1 plus c, right? Which is what we've been describing this whole time. Okay, so some extra rules here, similar to what we saw before. And so some extra ones we didn't talk about, cosecant times cotangent and so on. So please, these are some more identities to help you solve some of your problems. All right, this is from somewhere else. Again, I'm trying to find as many of these examples as possible to help you. So again, if the derivative of e to the x then is e to the x plus c, the derivative, sorry, the antiderivative or integral of 1 over x is ln x plus c, and these are some additional things that we've seen before. So just another way of writing the same stuff. I've also put this in just in case you want to add this in on your own to your cheat sheet. All right, so, okay, this is interesting. So we say that we want to find f prime at x, right? If f prime at x is x squared, and f at 0 is equal to 5, find f at x. So what is this actually saying to us? F at 0 is equal to 5. Well, that's really the c, isn't it? Right? If f, or the original equation for position, is x squared plus c, x squared plus c, right? And when f is 0, when the value for the x value is 0, that means all we have left is c. And if c is equal to 5, that's your constant, right? So when we're saying this, is we're saying if I say f at 0 is equal to 5, I'm actually saying that your constant is 5. Think about this for a second, right? So x squared then would be, if f prime at x is x squared, let's do that part first. So what is f at x? So the antiderivative of f prime at x, right? Well, then it would be, okay, so I add 1 to it. So 2 plus 1 is 3, right? And then I take whatever the 1 is, the phantom 1 in front of the x, over 3. So 1/3 x to the third, right? 1/3 x to the third would be that part, right? Plus c. And we know when f is 0, then c is 5, right? So we can find that the total f at x itself is 1/3 x to the 3 plus 5, where c is equal to 5 in this case. Would you see that? So that's how we can solve for the constant, right? When we have a value, right? When we're saying what happens when f is at this value. How come when what happens when f is at a different value though, right? We can still find the constant, but now it's going to be some other way of doing that, right? So if I have a value, if I set f at 1, what would that be? So again, I have this complicated looking equation, something over something x to the 3, and I want to find the antiderivative, right? So this is interesting. This looks like an equation that I can multiply to get back. Now, how do I do the antiderivative of this one? Can anyone see this one? I got something over something, and I want to find the antiderivative. Is there an identity from the previous pages that I could use? Because it's something over x to the third, right? Okay, and then multiplied by x to the 5th plus 3x. So I got to find the antiderivative here. I think I'm going to handle this one in lab because I'm going to break it down a little bit more for you. It takes a little bit of time. Yeah, I could split it up into 2 terms. It's one way of doing it. I could do that, right? And then I want to kind of find if f at 1 is equal to 1/3, f at 1, then I sub in 1, right? And I know that on the left side it's 1/3, right? And then I can find the constant by doing some manipulation. some other manipulation on the other side, okay? So I can find the constant that way. And then I can find f of x, okay? All right, so this is called the fundamental theorem of calculus, all right, where we have a range of values, And this is where people get totally messed up again. So a couple areas. And when we have this symbol here, where we have an integral from one value to another, let me just bring this a little closer in so you guys can see it. That's a lot closer in, but anyways, you have this thing. The way you would read this is, you know, you want to go from where the value of t for time, as an example, might be 0 up to 5. So where t is equal to 0 or t is equal to 5, I want to find this integral. This is a great way of finding area under the curve, right? So I know that I start at 0. I want to find part of the area under the curve. From t is equal to 0 to t is equal to 5. By the way, this goes back to one of your questions on the assignment, right? Where I've asked you to find different parts, area of under the curve, you know, of the, I think it's the Hyperloop train, where it speeds up and slows down and stuff like that. So what I'm really saying is here, take the position, right, at time 5 seconds and subtract from the position at time 0, and you're going to have the total area from within that range. That's what you're doing. So actually you're doing the integral twice, right? Where finding c is going to be, you're going to find c at different values, okay? So that's the kind of fundamental theorem of calculus, why we use calculus. And as an example for this, where you have, you know, if g at x is equal to a, the integral of a to a from a to the x, for any time t, right? Then g prime at x is equal to f of x, right? Whatever f of x is, right? But what you want to do is you want to take the first value, as an example, and subtract the second value for most times. Okay, that's what it is. So you basically find the same equation, the same antiderivative, use the same antiderivative with different values. So going back to that then, if this is the case that we're looking at, we're almost done, guys. I'm sorry. I know this is hard to follow sometimes. So here's a case where I have the integral from 0 to 1 of x squared. Okay, 0 to 1, where time is equal to 0, from time is equal to 0 to time is equal to 1. It's only one slice of the area under the curve, right? From those two intervals, right? That's what I'm looking at. So I know that the antiderivative by itself is equal to 1/3 x to the 3, because if it's x squared, if the integral is x squared, right? The antiderivative of this would be 2 plus 1 is 3 on the exponent side. And then you take 3 and you divide it by 1, the phantom 1 that sits in front of all numbers, right? 1/3 times x to the 3. So this is the antiderivative. Okay, now I substitute. I first take the higher value up here, substitute it in. So this top value is what I use first, minus by the second value, right? And then notice that there's no c here. I don't have a c because I have values. I don't have to figure out what the constants are, right? In this particular case. So I take this, so 1, anything 1 to the exponent whatever is still 1, so that's 1/3. And then 0 to the some exponent, as an example, would make this 0, right? Which leaves us with 1/3, and that would be the answer. Okay, so the total interval of at time is equal from 0 to 1 in this particular case. If x squared was describing the velocity function, right? Then the total distance traveled would be 1/3 of a unit, whatever that unit is, okay? Here's another case, right, where we have a 1 and a -3, okay? You do the same thing. So first, you describe what the antiderivative is. So 3x plus 2, right? Notice that there's no c in this case, okay? You take, again, x, add 1, you have x to the 1, really, is what you're doing, plus 1, so x to the 2. And then you take 2 and you divide 3 by it. So 3 divided by 2, x squared, plus you have 2 and you add an x to it because that's what you would get. That is the antiderivative without the c. And then what you do is you sub in the values. You take 1, you sub in the value for 1, and then you take -3 and you sub in the value for that, and then you figure out what this is. You kind of subtract, so 3/2 plus 2 as an example, right? Minus 27 over 2 minus 6, and then basically what you do is you simplify. For these ones, remember I told you not to simplify for the derivatives and all that kind of stuff? When it comes to numbers, and there's two cases I want you to simplify. One for limits. Limits, a lot of times you get a value, like 1/3 or 3 or -1 or something, right? And here, when you do this range of integrals is what we're doing, an integral range from some value of time to another value of time, as an example, or some value on the x-axis, as an example, then I want you to simplify as much as possible, right? So 3 over 2 plus 2, as an example, you simplify that, and then you do the rest of it. Okay, I just wanted to show you the steps. And it'd be the same for this one, right? The same for this one. So first we find the antiderivative. So that would be x to the 2, and then x to the 2 is here, and then 4 over 2. So 4 over 2x to the 2, which you could also say as 2x to the 2. That's what this part would be, minus. And again, I'd add 1 to it. 2 plus 1 is 3. 2 plus 1 is 3. And then 6 over 3 is 2. So 2x to the 3, right? Plus 1x. So that will be your antiderivative, right? And then you'd sub in 2 into the antiderivative, whatever that is. And then you want to subtract where the value is -1. And then you get values, actual numbers, integers, hopefully, or some kind of fraction. And then you find out the answer. Yes?
I don't understand why we don't have constant.
Because we're given the constant. We're given the value. One time slice, the values from yes. But in this case, we have a finite number because the constant would just shift us one over the other, and it doesn't matter because the constants will cancel out. All we're looking for is the area under that curve for that interval. We don't care about the extra work, the extra stuff, right? So yes, physically we'd have that plus c, but we're looking to find the area, only the limited area, the time slice, if you will, from -1 in this case to 2. The other stuff we don't care about. There's more, but we don't care about that part. But it doesn't matter. Even if you shift it this way or shift it this way, it's going to be the same area under the curve, right? You see what I'm saying? So even if I shift it this way to the right, it doesn't matter how much I shift it. I can shift it 100. Still the same area, right? The curve might be drawn over here,
Okay,
right?
let's say the interval is between -3 and 1, right?
-3 on the left and 1. Okay, that's the interval, right?
And let's say we also have a constant.
Who cares? So now it's going to be it's not going to be shifted.
The graph being -3 and 1 is going to change now because we shifted it.
Yeah, not really though, because the only thing you're shifting is on the x-axis. The graph is what you're describing here when you take the antiderivative, right? So the graph isn't going to change because you're subbing in values, right? And you don't care about how it's going to shift the values because at the end of the day, the area under that piece of the curve, that piece is going to remain the same. So that's why we can ignore C.
With the graph is the idea.
Yeah.
So it's not like you're moving the area around.
Yeah.
But like if it's declining, you're not gonna start checking the low end instead of the top end. The part you're checking moves with it.
Does that make sense? So remember, we're only adding a constant.
I don't see
We're not.
how
We'll do it in lab. So we're adding a constant. We're not adding another formula, right? If I was adding something else like x squared to it, and that was some other thing we don't know, yes, you're right. It would be changed every x, right? But in this case, we're just adding a value to x. 1, 2, 3, 100, 1,000. It doesn't matter. The area under that curve is just going to shift somewhere, one way or the other, on the x-axis, right? Okay, so that is some parts of it. Let's talk about the next part. And my friends, this is the hardest part of calculus. So please pay attention now, all right? If I have integration by parts, there will be maybe one question on the test this way, all right? I'm just letting you know. This is the hardest area that you have to deal with. And you're going to go, what the heck is this? What the heck is this, right? Where u and v are functions of x, and and both of their derivatives exist. So the derivatives have to exist for this function to work, right? And it's almost like I have some, integral of u at some v. So it's not anymore at x. It's not u at d, the derivative of u dx. It's not like that. Notice before, when we had the derivatives, we would write a dx on the end, right? With respect to is how you say it, with respect to x, right? Well, guess what? There's no x here. It's u with respect to v, right? Some other value, right? Which is almost like having two different equations, two values or two different things altogether, right? And so what you do is you take u and multiply it by v, the two formulas, minus the derivative, or sorry, the integral of, the antiderivative of v with respect to u. Okay? Yeah, this is where we get nutty, right? So please, it's difficult. I'm not going to read this one. We're going to read it in class. So here's an example. So I have this antiderivative of x to the ex. If we see that u is x, and this is almost like taking the anti-product rule. Okay? So imagine I had the product rule, and I got some derivative from it. And now I want to find the antiderivative of a product rule. Or worse yet, the antiderivative of a quotient rule, right? Yeah, I want to work backwards from the product. Remember, the product rule and the quotient rule are the most difficult parts, if you think about it, other than the chain rule. By the way, you can have that too, right? So some kind of chained thing that's a function within a function, right? By the way, this is the hardest we're going to get. It's not going to get harder than this, but this is something we have to think about. So how does this work? So we have to take x. If we substitute u, x is equal to u, and v is the other function, right, which is e to the x dx. Notice how they pair e to the x dx together, right? Because this is one part and x is another part altogether, right? Where x is not x with respect to dx. It's something else, is what they're thinking, okay? And if you think about this, if you want to take the integral of this, right? And by the way, you could also do it the other way. You could say that e to the x, there's a bunch of ways you can define u, right? And you want to find the best way to define u. And this is sometimes what happens when we look at a problem, we're like, oh, I made u the wrong one, whatever that wrong one is. Like, here's the wrong one for me. This would be crazy to do u as 1 and dv as x, e to the x, with respect to dx. That's crazy. That doesn't help you, right? This kind of helps you out, this form, right? This one might help you out, okay? Because you can say it this way as well, where u is e to the x, not u is equal to x, right? With respect to x. I don't think this helps me out either. This one doesn't help me, and this one doesn't help me, but these two, I can do something with them, right? Because then I can apply the formula that I just showed you up here, right? This uv, right? And when you say u, this kind of italicized u and italicized v, right? As an example, that is the antiderivative of u and v, right? And then I'm still going to have this integral left over. So I have one part that is the antiderivative, and another part that I still have left over as the integral. Okay? Okay. I'm trying my best here. And this has always been the most difficult part to explain. So if you think about it, here's an example of this. All right? So if we say that let u, I'm going to bring this a little closer up so you can see it. If we say that this is the original equation, right? So I want to find the antiderivative or the integral, you can say it both ways, of x times e to the x with respect to x, right? dx. Then if we say that u is x and dv, right, d with respect to v is e to the x dx, all right? So that's what we do first. We kind of assign these values. Then u is equal to the x, right? du, right, du is dx. We're going to come back to this in a second, right? So derivative of u is derivative of x, right? And v by itself is e to the x. Okay, this is just the way to parse it, if you will. Then dv is equal to e to the x delta x, or dx, which is this part. And now we just sub in. So if you look at this, if you use this equation, which is the equation we presented earlier, right? And you sub in these values. So u, right, that's x. dv, right, is e to the x dx, right? And that's what you put in here, right? So u dv. And And then you have the integral, right, of v, which is e to the x, times dx, which is du. Du is dx. And then you'd have this situation left over where you continuously go to the next level. So this is the first step is finding this piece. Once you find this piece, you continue with the integral, right, until you get to this piece. Notice we get c back, right? So when I have the antiderivative of e to the x, it's just e to the x, right? Because e to the x got us to if the derivative of e to the x then would be e to the x, and then we add c to it. So it's like what you want to do here when we want to do integration in parts is we want to use this pattern, all right, which I recommend putting on a cheat sheet, and I'll have it on there for you, and subbing in different parts of the integral, right? So you can figure out this part right here, okay? Does that make sense? So instead of trying to understand everything, which is something what people do, right? If you sub in those areas, right, you will get the answer that you want. And it's for these complicated questions where you had some kind of product rule or quotient rule from a derivative perspective working on these things first, and you want to get the antiderivative of a product rule or quotient rule. Yes?
Why are we leaving the BF and the DX in the second part and then just kind of removing
Well, you're not removing it. You're actually, it's just the second step. So the first step, going back, I like your question though. So the first step is getting to this.
Yeah.
Right? Once I use, if I have this, the first step is getting to here, but I still have this integral, right? And for me to get the first antiderivative, I need to get rid of the integral, which means I have to integrate that one piece, right? But leave the u and v alone, right? So if I go back to the example, which is this one, u and v then would be x and e to the x. That's the original two. So x and e to the x is the original two formula, right, that I multiply together and subtract the integral of v, which is e to the x, the second one, right, with respect to u, right? But when we say respect to u, we're actually saying in this particular case, it's going to be respect to x, so we drag this down. So actually what we're doing is the exact opposite of the product rule here. Remember the product rule, how it works, right? We're saying that it's the derivative of the first times the second plus the derivative of the second plus the first, or times the first, right? And what we're doing here is we're trying to go the other way around plus adding c to it. So first we get this piece, which is taking the original two formula, multiplying them together. That's what we're getting here, right? And then subtracting the integral. Huh?
We're timing that by times the dx by the derivative of v, which is dx. So the
Right.
dx's cancel each other out and dx.
Yes, yes, and that's how you get this, right? Now, here's one step further. Some people have done, they've taken it further than this on a test, and they said, well, can't I factor out the e to the x? And if you did that, if you factor out the e to the x, and I wouldn't recommend you going further than this, but if you really wanted to, it would be e to the x times x minus 1 plus c, if you see that, all right? That would be your answer. And if you think of it that way, then you have two equations, x minus 1 times e to the x. And when you derive that, you would want to use product rule, right? First equation times the second equation, right? And you want to find the derivative. That's why we're doing integration in parts for that particular case. Does anyone understand, or is this as clear as mud for most people? Mud, I know, it's mud for most people. Huh? You kind of have to, I know, we have to do it in lab. If we do it in lab, we'll do some more examples and you'll understand.
I just have a question about
Yeah.
Can you go back to the slide?
Yeah.
So when we assign values,
Because we're going to the antiderivative, right? du is d with respect to u, right? With respect to u is this with this thing, right? So what we're trying to do is we're taking the antiderivative of x and the antiderivative of e to the x, right? But the problem is it's, you know, we have this complicated thing, and so we say we're assigning d with respect to v, some other antiderivative which we don't know about, kind of thing, because there's also a plus c to it. We're just assigning a variable name, if you will, a label, right? These are labels. So u, now we're letting u be x, and we're letting dv be e to the x.
Yeah,
And when we,
that. So let's say if u was equal to x squared, then du would be 2x dx.
yeah, let's go there. Let's go there. I want to show you some examples here. So let's go to this. All right. So here we have, if we said that u is equal to x squared and sine x is equal to sine x dx is equal to dv, right? That whole piece, right? Then we would apply the formula here, okay? Which is basically just taking x squared and the rest and getting this next part back. I'm going to give you some examples in lab about this. I'm also going to show you this stuff online, right? Because sometimes what happens online is people will be looking online for your assignment, and you're going to see some other piece parts to it. And there's some equations online that they use other identities, right? And I want to show you those things when we're in lab together. Okay, and here are the examples from this point on. So basically what we're doing is like, here's an example, and I want to talk about this first one. So let's think about this before we go to lab. The motion of a spring subject to dampening force is described by F at t, where t is time, is equal to E, Euler's constant, to the negative 2t sine 3t, right? What is the velocity of the spring at time t? All right, so what the heck are we asking here, right? This, when we talk about spring, is acceleration. That's the first thing to note, right? The motion of a spring and the dampening force is almost like negative acceleration of the spring as it continues to dampen until it stops. By the way, hint, hint, your Spider-Man question doesn't dampen, right? Which is probably one of the problems of Spider-Man in the assignment number 1, right? So here we have actually acceleration, not, we don't have velocity. And what I want to do here is I want to find velocity, so I have to take the first antiderivative of this equation to find the velocity equation, which means I have to integrate from this thing. How do I do it? What are the steps that I do? Do I do integration in parts? So I have this one formula multiplied by a second formula. And that should kind of be a hint for you that that is something that I need to do. Okay, this is integration in parts, right? Because I have e to the negative 2t, that could be u, and then I have sine 3t, which could be dv. And there's your integration in parts. So we're going to think about that. That's one way of doing it. You could also move it around the other way, and sometimes it makes sense. You might try this out. We'll try it a couple ways in lab, where we say u is actually sine 3t, and dv is actually e to the minus or negative 2t dx, right? And that can actually move around the equation, because if you remember, you can move around the relationship with u and dv to any part of the integral, right? So the first part is ex and ex, so this just seems natural, but actually you can make it the other way around. Or you can also assign 1 to it, or you can make it so that it's u and dv. You can do any of these forms, and sometimes one form, when it comes to integration in parts, is more advantageous for you to use than another form, okay? If that makes any sense. So that's one of the questions that we're going to cover in lab. And the other ones are find the derivative of y is equal to sine cos x squared. And this is what I mean here is the antiderivative, how do I go up one? Here, right? And the other one is find the antiderivative of a range of numbers. One of them you're going to get is pi over 2 radians, okay? You're going to get that. But it doesn't really matter, does it? You just keep the units. So pi over 2 as a good example, right? And then you would just sub in these values, pi over 2 and 0, when it comes to, with respect to sine or a trigonometric function, makes sense, right? So you can do that. But remember to use radians on your calculator, right? Which is important. Okay, again, you've got this. This is definitely integration by parts, okay? And here's one that always messes people up. A car braked with a constant deceleration of 16 feet per second squared, right? What is a constant deceleration? it's the second derivative of position, right? I'm just giving you the relationships from a physics perspective. Producing skid marks measuring 200 feet. I have some kind of C value. There's the C value, 200 feet, right? Before coming to a stop, how fast was the car traveling when the brakes were first applied? So now I'm looking for velocity and position, right? So if I go one antiderivative up, I can see that 16 feet per second is a constant. That means I need to take the antiderivative of 16. And what's the antiderivative of 16? And we'll go from there. I'll cover. Yeah, exactly. We'll go up from there. Plus C. Right. And we'll talk about what that means. Okay. So any questions around integrals? I know this sounds like that's it. There's nothing else to it. Yeah. There's nothing else to it until you start doing questions. And then you're like, wait. And I'll try some other ones too, some really easy ones with you guys too, just like to get back to the antiderivative, the first antiderivative. But it looks a lot easier than it is. And we're also going to cover the chain rule parts. How do I get the derivative of this thing when I have to use the chain rule? I want to talk about that, okay? Any questions around today? So today we had two parts. We had the chain rule and we had integrals, okay? And I want you to remember the integrals are area under the curve in many ways. We want to find the area under the curve or the total distance traveled or the total velocity with respect to a particular time frame. All right, for those people who didn't have a chance to sign in, I'm also going to bring up the class right now, but I'm going to stop the video. So please log in if you haven't had a chance to do so.